So, got it. Right. So how does fluorescence being and phosphorescence produce? So we have discussed this electromagnetic spectrum. Okay, everybody by now should know how UV and visible region here, UV here. Okay, this probably the other way around. This is lower energy and this is higher energy. So this one shorter wavelength, this one longer wavelength. But you can also view sometimes the spectrum the other way around. You just have to check whether they are using starting from positive scale to negative scale. So what I'm talking about is this region. We have discussed atomic emission, atomic absorption, which happens here, ultraviolet and visible region. So what is fluorescence? So fluorescence also is in this region, okay? But it is not ultraviolet, it is not visible, okay? So we have discussed atomic absorption, and then we have discussed about the problems, the sample preparations, and some interference in terms of getting a good accuracy. And we also have discussed emission, right? Emission spectroscopy. And we have discussed the emission is more robust, okay? And of course, we have, if we have inductively coupled plasma, atomic emission spectrometer, even though it is much expensive, but then it is versatile because you can analyze many elements at one time. Yeah. So I hope that you understand why AAS, atomic absorption spectroscopy, usually used for a single element, whereas ICP AES can be used for multi-elements at one time. Okay, so even though fluorescence is one type of with much better sensitivity and selectivity, right? But it is seldom used because it's quite limited. So we know already that in order for certain chemical compounds to absorb ultraviolet as well as visible, especially organic compounds, yeah, they require certain structure. So if it is organic compound, they requires the chemical compound to have double bond, or we call it chromophore. Okay, so that one I think I didn't discuss with you, okay, because we focus on metal, right? But if we are to analyze organic compound in UV and visible region, okay, they need to have certain functional group, okay, and usually it is called chromophore for them to be active in visible and UV region. Okay, so we talk about fluorescence. Okay, the compound that is active in fluorescence is even more less. Yeah? The number are less than the one that is active in UV and visible. So of course means that the option to do fluorescence is less than those compounds that is active in visible and UV region, but it is very selective. So how does it happen? Yeah. So this one we have, all right. I hope that you have mastered all this. This is electronic excited states. You have the ground state. You have the n equal to 1, n equal to 2. Yeah, this is what we call as electronic excited states. Yeah? And among this, between these electronic excited states, we have vibrational levels, okay? Excited vibrational levels. So this is what happened if the compound, okay, is received. If the compound receives ultraviolet, there is a possibility of molecule dissociates, okay, because of the high energy. But if it is just in a region of vibrational levels, okay, the atoms in the compounds, they only vibrates, okay? And you can see if it is in the region of microwave, they rotates. But we're not talking about microwave. Today, we are talking about electronic states as well as vibrational states only, okay? Before we can understand how fluorescence is being produced. Right? So this one, just to show you the vibration, the vibration of if that electron is at certain vibrational level, excited level. Yeah. Okay. So by now you should understand the electronic excited states and the vibrational level excited states. Yeah? So of course, the energy difference here are lower compared to the energy difference between electronic excited states. Okay, next one. Okay, this one, I will give you the revised version of the slides. And this one has a very good animation on how fluorescence and phosphorescence produce, but let us discuss here. Right, this is the most important diagram. This is the most important diagram, okay? In order to understand how fluorescence and how phosphorescence is produced. Means that, remember the picture just now? So how, right? Yes, everybody. Okay. How's the phosphorescence and fluorescence being produced? Okay, now let's talk about the electron here. So electron here is at ground state. Yeah. And here S1 represent the excited electronic level. Yeah, this is the one. The excited electronic excited states. Yeah. So this is ground electronic states. This is electronic excited states. All right. And this one, okay, S1 represent the electronic excited states 1. And then S2 represent the electronic excited states 2. Okay, what happened to the electron? Okay, of course, we know already if given enough energy, specific amount of energy from the ground state, electronic ground state, it can be excited to electronic, excited electronic state. It can go to S1 as well as it can go to S2. Depends on the energy given. So let's say the electron goes from S0 to S2, let's say. And due to some reason, okay, let's look at the explanation just now, okay, right? Due to some reason, right? So absorption of UV by molecule excited from vibrational, okay, from the ground state to the electronic excited state. But there are things that can happen to the electron, okay? It does not necessarily, it goes down to the ground level, okay? What I'm saying is, most of the time, not to say most of the time, what we have discussed before, yeah? We understand that when the electron goes here, the electronic excited state, and it will undergo relaxation and go back to the ground state. Okay, once it goes to the ground state, it emits energy, which is in the region of either UV or visible. So that's how UV and visible region is produced. But what happens if the electron decides not to go straight away to the ground state? Well, the electron can do that. Electron decide not to go to the ground state. Instead, it might jump. Okay, you can see that the electron now, this is excited state number 2, electronic excited state number 2, which is higher energy. It can jump to electronic states with lower energy. And then it jumps slowly. You can see here, it jumps slowly. Okay, I think I'm using present pointer pen, probably, all right? So this one, you can see the electron jumps, or not to say jumps, goes down slowly. It does not go straight away to the ground state. So it go down slowly in the vibrational level, excited vibrational level. Okay, so I hope that you now know this is electronic excited states, and the thin line represent the vibrational excited state. So the electron now decided to go down slowly instead of going down abruptly. So after the electrons reach the lowest vibrational state here, then it goes down to the ground. And even here, you can see that the electron also can decide from here straight away to the ground, or from here decided to have one more step of the vibrational level of the ground state. You can see that it can also go down very slowly. So this relaxation, vibrational relaxation, does not emit any obvious photon. So here is where the infrared region. That's why if you using infrared, because people are using, you put infrared in clothes, you put infrared in your bed, in your pillow, you feel the heat, right? You feel the heat. So it only release heat, but it does not really release a significant photon, means that a significant energy. So IR is actually a very low energy. So you can see now that before the electron is being released to the ground, okay, it is, of course, requires energy to be excited. So this is the absorption of energy. Okay, of course, it is specific, but it decided to slowly goes down, like going down some steps first, small steps, before it goes down to the ground state. So now the energy level of the electron okay, is different than the energy level that has been absorbed before it gets excited. Okay, that's why you see the lambda is different. Okay, so the one that produced by the movement of electron from the lowest vibrational level to the ground state, it is called fluorescent. Okay, so it's not UV, it's not visible, but instead it is called fluorescent. So this one, it is called internal conversion, means that from the excited, electronic excited state S2, it can go to another electronic excited state, and it goes through a vibrational relaxation. Okay, this is called internal conversion, the transfer. And this vibrational relaxation only emits IR, IR region. So there is no significant like spectrum that you can observe. And then when it goes down to the ground, you will observe fluorescence. Okay, so fluorescence is the picture that that I showed you just now, the beautiful picture. So that's how you get the fluorescence. And what is phosphorescence? Yeah, phosphorescence. So the electron from here, from the vibrational levels here, can also decide to move into a third system. Yeah. So this is singlet excited states. Okay. And the electron can decide to move to another excited states, but higher vibrational level. Okay. Lower electronic excited states. You can see S2 higher, S1 lower, and probably a lower excited states, but higher vibrational states. Okay, and it is called inter-system crossing. Okay, so again, the electron probably decides not to go down yet, so it goes to another vibrational of different electronic excited states, and slowly it goes down. And if it decides to, and finally, if it goes down to the ground state, now we have what we call as phosphorescence. Okay, so it's easier to understand that the first step is electron receive energy and excited from S0, the ground state, into higher electronic excited states. Okay, so it can happen that the electron will do internal conversion. It moves to lower electronic excited states. Okay, and then moving down slowly through different vibrational level. And at this moment, it only emits IR region. And finally, it goes back down to the S0. And this is where fluorescence will be emitted. And another process that can happen to the electron, it can go through inter-system crossing. Okay, it will go to another electronic excited states. Okay, another vibrational level, and then it finally move to S0. We're gonna have what we call as phosphorescence. So let's look at the explanation. Yeah. Right. So this one, the one that I mentioned about absorption of energy. Okay. And now it is in excited state, singlet state. The molecule can then undergo vibrational relaxation, inter-system crossing, which is caused by a radiationless transition. Okay, so I don't know, it is not considered a radiation, but probably because it is low energy. So what can trigger this? What can trigger this? Number two, okay, is because of the collision. Okay, so probably you have another molecule in the system, so they collide. So there is some interference on the vibrational energy. So that will trigger the electron to move, to go down slowly, steps by steps, using the vibrational energy level. Okay, once the molecule has reached the lowest vibrational state here, right? The molecule will release a photon of less energy than the absorbed, yeah? Because you can see there is a difference. Here absorbed, and here being released. The amount is different, and of course the lambda is different. And to return to the ground state, giving a wavelength of the visible spot is seen as fluorescence. Yeah, right. So phosphorescence, what's the difference between phosphorescence and fluorescence? Okay, we have this explanation here. I think I put it here. Okay, when the molecule excited singlet state, another possibility it can occur through collision. The spin quantum number can be changed, producing excited triplet state. Okay, so what's the biggest difference between fluorescence and phosphorescence is the change in the spin number. So I don't know whether you have studied that electron has one set of orbital number, okay? So they have N, L, MS, and N, L, ML, and MS. N is the electronic state. ML is the orientation, like SPDF, okay? MS, which is, ML is the magnetic spin, okay? And MS is the spin, whether it's clockwise or anti-clockwise, okay? So for fluorescent, there is no change in terms of spin, okay? Electronic energy transition that is responsible for fluorescence does not change in spin, electron spin. So the fluorescent is faster in terms of production, okay? So which results in short-lived electrons in the excited state of fluorescence. Means that you get fluorescent faster, quite easily. Whereas phosphorescence, there is change in electron spin, which results in a longer lifetime of the excited state. What does it mean is if the electron triggered to have this process, inter-system crossing, moving to the triplet excited states, the electron will stay here longer before moving to the ground, producing phosphorescence. So actually phosphorescence usually called a delayed fluorescence. Okay, so you will get fluorescence first, and after sometimes if there are trigger or intersystem crossing, you will get phosphorescence. Yeah. So I hope that after this you can at least view this YouTube. Okay, so that because there are animations, so that you can understand much better, right? So that is how the process of producing fluorescence as well as phosphorescence. So this diagram, it is called Jablonski energy diagram. Same goes with here, but this one is much simpler. You can see how the excitation, and then you have internal conversion, and then you have fluorescence, a possibility of intersystem crossing, okay, internal conversion, and then you have phosphorescence. So these are the processes that happens. Yeah, make sense? Make sense to everybody? Okay. Any questions? Right. Okay, so these are the detail if you want to go through what is vibrational relaxation. So this is just a repetitive, but you know, in more detailed picture, right? Internal conversion, what happened, and you know the dissociation of the atoms just now. Okay, because if you are using just IR, there is no dissociation of atoms, okay? Only the vibration, right? So fluorescent, so if we are talking about UV or visible region, visible region especially, we're talking about Beer-Lambert's law, right? to quantify, to do some quantitative analysis. But for fluorescence, in order to measure how high is the fluorescence efficiency of the molecules, yeah, it is using the term quantum yield. Okay, so this is the formula. So whatever represented here is the process that is happening during the production of the fluorescence. Yeah. So no need to worry, because I'm not going to ask you to calculate this. But in order to, if you like, synthesize a new compound, okay, which has a fluorescence properties, you have to calculate the quantum yield in order to quantify how efficient the fluorescence properties of that particular compound. Yeah. So this one done. So I'm showing you the example of three spectra, three spectrums, three spectra. Okay. This one is ultraviolet region, UV region spectrum. And this one is fluorescence. Okay, you can see that the fluorescence is actually in the visible region, right? We know that visible region is between around 300 to 800. So fluorescence and phosphorescence actually in that visible region, but it is caused by different kind of process, okay, due to the electron moving to the moving down slowly using the vibrational states. Yeah, so you can see there is a significant difference. It should be, yeah, should be there a significant difference in terms of wavelength of UV region and the fluorescence wavelength, as well as phosphorescence. Okay, in order to have this fluorescence spectrum, we need to do some analysis on the excitation wavelength. Okay, so let us move to the example straight away before we can understand. Okay, so I think I have. Right. So you can see here there are two spectrums. Okay, spectra, right? Before we can get this fluorescence spectrum, okay, the right side, we have to decide on what is the excitation wavelength. Okay, because if you don't excite the electron with the right amount of energy, you will not be able to get the fluorescence. So when you do fluorescence study, or if you're using fluorescence spectrophotometer, there are two wavelengths that you have to decide. No, there are two wavelengths, which is important, what we call as excitation wavelength, right? And the results that you get is called emission wavelength. So excitation wavelength and emission wavelength. Okay, so if you don't choose a correct excitation wavelength, you will not get a good emissions wavelength, or if you will not get a good emission spectrum. Okay, so the selection of excitation wavelength is very important. So let's go back. Right, so these are examples. Okay, these are examples of fluorescent compound. Okay, so you can see that commonly fluorescence, they have this benzene ring. So fluorescent, those compounds that are active in fluorescence, they have this benzene ring. So why we need all these double bonds. So you can see the double bonds are alternate. Okay, so the electron is delocalized, means that the electron is more free to move around the double bonds. When you have these conditions, the electron is delocalized, and so the freedom of the electron move is higher compared to those here. Okay, so you can see that for fluorescence, okay, so even though you have chromophores, right, but it does not mean that it can exhibit fluorescence. So they are more rigid. Yeah? They are more rigid structure that can give out fluorescence. So sometimes that's why fluorescence, even though it's very selective and sensitive, it's not commonly used because of the limitations. Not all compounds will exhibit strong fluorescence. Yeah? And sometimes fluorescence increase for chelating agent bound to metal. So this one I do observe. These are chelating agent, call it chelating agent, or sometimes we call it ligand. When we bind them with metal, certain types of metal, they sometimes increase the fluorescence intensity, means that the fluorescence are getting higher in terms of intensity. I don't know what kind of metal, what kind of interaction, I don't know the theory of how it increase or it does not increase. I don't know that part. But chelating agent, of course, because it is with, you can see here, oxygen with lone pair, nitrogen with lone pair, it can react with, it can form complex with metal ions, okay? And this whole thing might have an increased fluorescent properties, but I don't have the knowledge of how it increased. Okay, but I do have experience when I add when I add metal to the ligand, it does increase the fluorescence. Yeah, right. So as you can see, it's very the compounds that fluoresce is quite limited. But commonly you can see if you have a lot of benzene ring, it is called here benzene ring, there is a big possibility that it has a high fluorescent efficiency. It fluoresces strongly, yeah. Okay, but there are of course external factors that affecting the intensity or the efficiency of the fluorescence. Okay, one is what we call as heavy atom effect. So if you have halogens like chloride, chlorine, iodine, fluorine, okay, in the solution, yeah, if you run, if you test the fluorescent properties and you have these halogens in the solution, they can decrease, they can cause decrease in the fluorescence properties of the compound that we are studying, yeah, due to the possibility of absorption of the energy. It will interfere with the energy, therefore the fluorescence is affected. So if you are to do quantitative analysis, you have to degas. If you have the sample, you have to purge with nitrogen, okay, to remove halogens as well as oxygen. Yeah? Oxygen also interfere with the fluorescence intensity. So we do not want this to happen, as well as there are issues when you increase the temperature. So the quantum efficiency, the quantum yield just now of fluorescence decreases with increasing temperature. Due to increased frequency of collision at elevated temperatures, the probability for deactivation by external conversion is improved. So if you go back, what does it mean by external conversion, which I didn't share, if I didn't discuss with you just now. So what is external conversion? The activation of an excited electronic state may involve direction and energy transfer between the excited molecule and the solvent, means that there is energy going out, yeah, from the compound to solvent to any other interfering ions in the solution. So this one will cause the will cause the fluorescence to lower down, okay, and the process of the lower down of the fluorescence, it is called quenching. Yeah, the word quenching is describing the lower down of the fluorescence intensity. So this is what we usually don't want, and so try to avoid heating up the solution if you are working in fluorescence. If you want to analyze using fluorescence, so make sure it is at room temperature. Okay, and of course, just now you know that the energy might be transferred to the solvent, so this also will decrease the fluorescence intensity. Okay, so these are among the factors, but the biggest one that interfere is this one, yeah? Halogens, oxygens. So that's why we have to degas the solution. Okay, so this is how it looks for spectrofluorometer. And this one is how it looks for atomic fluorescence spectrometer. Because we learn about atomic absorption spectrometer, we learn about atomic emission spectrometer, and this one is atomic fluorescence spectrometer. Okay, and you can see that the biggest difference, the biggest difference, if you remember, when we talk about AAS, we talk about AES, is always parallel. Yeah, we have the light source, we have the atomizer here, and we have the sample introduction, and we have the detector here. It's parallel. Of course, we have the monochromator, beam cutter. I think is always parallel in one line. But for fluorescent, the location of the detector is 90 degrees. You can see this is the light source, this is the sample, the supposed to be the sample, but the detector is at 90 degrees. Why? Because this actually narrow down. Yeah, we can see that there are so many other emissions that can happen, but for fluorescent, that's why it is much more selective and much more sensitive. The filtration of the whatever being produced is much more selective. That's why by using fluorescent, you have reduced amount of interference. That's what the beauty of using fluorescence, but it's hard to get fluorescent properties. So this is a setup of atomic fluorescent spectrometer. Okay, right. So in here I make it larger and simpler. So the detector is here. You can see this is the sample. It is 90 degrees. Okay, and for spectrofluorometer, not atomic fluorescent spectrometer, but I think it is also good that you know about spectrofluorometer. This is the light source, okay, used for to have fluorescence. Okay, the light source usually are different from ultraviolet and from visible. Okay, and you have a monochromator. Just now, remember that we need to come up with a proper excitation wavelength, right? So the monochromator will give you the possibility of choosing, narrowing down the lambda for the excitation wavelength. And of course, the process happened here. You introduce a sample, blah, 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 and you have 90 degrees. And then another monochromator is the one that narrow down the emission wavelength. Yeah, because we just now we observed two spectrums. Yeah, so excitation wavelength, and this is what we call excitation spectrum. But usually, the most important here is what is the excitation wavelength producing the emission spectrum, and what is the emission wavelength. Okay, so that's why you have two monochromators in here, because to select two wavelength. Yeah, right. So this is the example, okay, of fluorescent reagents. You have these are the excitation wavelength. Okay, so you can key in into the instruments the excitation wavelength, and then you will get the fluorescent or the emission spectrum. Okay, the fluorescence, and this is the emission wavelength. Okay, so when you study fluorescent properties of certain compounds, these two are very important to give a correct excitation wavelength in order to produce a fluorescent spectrum. Okay, with a specific emission wavelength. Yeah. So what's important is sometimes how do you know? How do you know which wavelength to use? Okay, for standards reagents, for standard compound, you can have the excitation wavelength from the literature. Okay, but for, let's say you have a new compound, you synthesize a new compound, fluorescent compound. So of course you have to do try and error. Okay, you have to do try and error. You can key in 400, 450, and look at whether you get a good fluorescent spectrum. Okay, so sometimes you don't get the fluorescence, so there must be certain must be the excitation wavelength is not enough, or probably is very low in energy. Okay, so you have to play around with these parameters. Okay, right, and that's the last part for fluorescent. We look at the example of the usage applications. So I think many of you know about Alzheimer's disease, okay, which trigger dementia. Okay, of course, this is one of the worst scenario. We don't want to be in this condition, but unfortunately, until now, we don't know how Alzheimer. I mean, we know the cause of the Alzheimer is due to the growth of protein, amyloid protein in the brain. Okay, we know the cause, but how the protein is triggered to grow in the brain, there is still a mystery. Okay, so we can see this is healthy brain, and this is advanced Alzheimer's. So once the Alzheimer's set in, dementia set in, so you know what happened, especially to those old ones. Okay, and what happened? What is the relation with fluorescence that we learn with the applications of Alzheimer? Okay, why it's not moving? Right. Okay, let me change something. Okay. So example of Alzheimer's drug. So these are the treatment, means that this drug can remove the amyloid protein from the brain. But drugs are useful to minimize the symptoms. But unfortunately, these drugs cannot be used. These compounds are only available for dead body, because the things about brain, they have this what we call as blood-brain barrier. Okay, why? Because it's supposed to like block from unwanted bacteria or whatever that we don't want to enter the brain. Yeah, that's what the purpose of blood-brain barrier. But once you have a disease in brain, we need to treat the brain. Even drugs cannot penetrate the blood-brain barrier. So that's the issue. So there are research on synthesis of new compound. Okay, so this is an example. The compound, I don't know how to pronounce, but it's NIAD4, can be injected through blood vessels and can penetrate blood-brain barrier to enter the brain. And this new compound can bind strongly to the amyloid plaques in the brain. Okay, so this compound is fluorescence. Okay, it's red fluorescence, and so you can view whether it goes into the brain, attached to the protein or not through fluorescence. Yeah, so the compound is fluorescence, so it seems that it works. And this is example, the fluorescence signal of NIAD4 is stronger when it binds to the amyloid plaques. So you can see this is they started to study the compound NIAD4, and this is when they study the NIAD4 interaction with the amyloid protein. Yeah. So this is one of the application of many applications of fluorescence, but in fact, fluorescence is very interesting because it is more sensitive and more selective. So it's good for you to at least get to know fluorescence. If one day you wish to produce a compound, you want to synthesize compounds, so it's good to know this technique, right? And the last part for fluorescence is about Stokes shift. What is Stokes shift? Yeah? So Stokes shift, okay, here, the presence of appreciable Stokes shift. Stokes shift is actually the difference, yeah, here. The difference between lambda of the absorption and lambda max of the fluorescence spectrum. So that is Stokes shift. The presence of appreciable means that relatively resolution is good, the separation, yeah? The separation of absorption spectrum and the emission spectrum is good, means that it is a Stokes shift. Is principally important for practical application because you can have a better quantitative analysis if you have a good separation of absorption and emission spectrum. Okay, so this is what Stokes shift, yeah, right? So I think for the second part of our discussion, okay, I wish to just pause for now. Right, spectral line is due to overlapping lines due to the contaminants. Okay, this is something that is common in measurement if you are working with actual samples. That's why actual samples we have to do some pre-treatment. There might be emission, absorption spectrum from contaminants, from the interfering substance. Yeah? So, but then here, the atomic lines are very narrow. I mean, you have seen the lines are very clear, right? So with specific wavelength. So usually it is not an issue, especially if you have a good AES, or fluorescent. Okay, if you have a good one, this should not be an issue. So to overcome this, if you have, you have to choose the right wavelength. For example, vanadium absorbed at this wavelength, which interferes with aluminium, then you can change. You can change the wavelength that is not overlapping. Okay, so usually the new version of instruments, they actually don't have this issue because now it is a good system. So a lot of study has been done, so they already knew what is the specific wavelength for certain elements that don't overlap with other elements. Okay, but the issue of scattering, because in the sample, as I mentioned, especially when you work with actual samples, there are some organic compounds in there. So when we atomize, like we burn the samples, okay? So we have solid particles called particulates. So those particulates can sort of repel the light, and you have stray emitted lights, scattering. So you have, well, this picture at least give you some ideas. If you bombard lights to some samples, if we have particles, solid particles, they will also repel lights. Then you have what we call as scattering. So that's why we have to work with diluted solution, means that low concentration solution, to avoid this issue of scattering. And also we can do blank measurement, means that the matrix itself, we can at least do some blank to zero the background effect, scattering effect. Okay, broadband is due to the inefficiency of the atomizers. Usually, when the sample is introduced, okay, the atomization process is not in one shot. So the rest of the sample atomized probably in a range of time, so that will result in a broadband absorption. So this one also especially interfere with the calculation of the concentration, quantitative analysis. So if we have an efficient atomizers, okay, then this is not an issue. So another thing is viscosity. I think viscosity means that the sample, if it is too viscous, then it's difficult to be introduced in one shot into the atomizers. Even though you have nebulizers, but due to the viscosity, then it might have some delay for all to be atomized at one time. So that's why we work with low concentration samples. Okay, this one, usually we don't have issues because now we have a good software, right? So another one is continuum source method. So this one, okay, as I mentioned, I will give you the updated version of the slides where you can watch the YouTube with animations. So at least you know how this beam cutter, okay, works, so that you can reduce the background effect, where you have what we call as background correction method by using a deuterium lamp and the beam cutter. So you have to watch this video because it's difficult to explain. You need to watch the video and understand how the background is being corrected. Okay, so I mentioned about Zeeman effect. So this is the, okay, it's actually Zeeman effect. Okay, so what happened is, this is the excitation of electron. Okay, and this excitation, of course, the electron will go down and you observe emission line. Okay, emission spectrum. This is under no magnetic field introduced to the system. But if you introduce a magnetic field, just like this one, you introduce magnetic field to the atomizers, okay? Okay, what happened? That there will be what we call a splitting. Okay, this splitting is well observed in NMR. Yeah, NMR really use this splitting process, so that you know the proton NMR. You can study the where the hydrogen is. Yeah? So what happened is the energy is split. Okay, you can have from single line to you have, as I mentioned before, shadow lines. I don't know, I call it shadows, but it is actually split into different energy. Right, so this is what happened. The process is due to magnetic field. Of course, there are some calculation how the magnetic field splits the one energy level into three energy levels. That one I think is beyond my capability to explain how the magnetic field split the energy levels, right? So in the middle, the lines in the middle remains the same energy as without magnetic field. So this is Zeeman effect. And also Zeeman effect is used to correct, yeah, the background, okay, what we call as background correction method using magnetic field. So I think the best way is to, I think I have, all right, I don't have the link. Right. I don't have the YouTube link for Zeeman effect. I'll try to give it later, right? So that is what, how it works. You can see with Zeeman effect, we can have, okay, we can check this is background only. This is background plus the absorption of the atoms that we study, okay? So this is to reduce the effect of background. Second one, apart from spectral, we have chemical interferences. Okay. For example, if together with the samples, we have other compounds or salts that have low volatility, so it will volatilize together, right? So what happened is we need to use these techniques, high temperature probably, release agent and protective agent. So I don't know much about this because I never had any experience using this. Okay, so right, so this is protective agent, EDTA, usually known as ligand chelating agent. So this will helps to reduce chemical interference from low volatile salts. Yeah. So this one you need to study if you have decided to, for example, study some metals. Then you need to study the procedures For example, here they add EDTA to avoid the chemical interference. So this one you have to do during the method development. And the other issue is ion. Okay, so let me explain by using this diagram. So we remember that we have to do atomization, removing the anions. Okay, so we expect that if you want to analyze sodium, okay, the sodium should be into excited state, but still in atomic form, but it is as excited atomic form of sodium. But instead, sometimes we have ionic forms. Okay, so this ion, it will reduce the conversion of atom in ground state to excited states because it's absorbed some energy, but different wavelength, but it will interfere with this process. So if we interfere with this process, the intensity of the spectrum, absorption spectrum, will not be what we call as represent the actual concentration of the sodium or the samples that we analyze, because now there is some interference from ions because ion absorb the energy. So what we can do for this one, we can add what we call as ionization suppressant. So this is example of ionization suppressant. Okay, this will suppress the production of ions, okay, and the being process, which is from the ground state to the excited state, will be the main process that happen. Okay, so that is among the issues. Okay, you can see that more ions, fewer atoms, decreased absorption. So we don't want this decreased absorption to happen because in terms of quantitative analysis, it will be not accurate. Okay, so this one no need. So I think we have completed all on the atomic spectroscopy, absorption, emission, as well as fluorescence. Okay, so any questions before we proceed to the assignment? Any questions? Okay. If there is no questions, I will proceed to the assignment. So let me